meters. And there are two meters, at least, two things that you want to know. There is a voltmeter and there is an ammeter. Okay, so let's look at one at a time. First, let's do voltmeter. This is one of those, meters, D-arsenal meters. As divisions in this, and then there is a pointer. And typically there is a current here. And this meter deflection gives voltage. Okay, somehow this is set up so that this voltage at the terminals. And there is one important concept here. This is referred to as scale current. The same thing. Now you also have all this full scale current is when the meter is points at the maximum division. Say if this is 0 to 10 volts, it's pointing at 10 volts. 0 to 100 volts, it's at 100 volts. Okay, this is at max value. This is this side you have min value. Okay, so this current is Fs. Okay, and then electrically this circuit is equivalent to this. This meter has a resistance Rm. Meter has a resistance, and then typically at max deflection when it is full scale, full scale. Full scale for meter. This bit is clear. So the deflection in the meter depends on, it shows the voltage and depends on the current that shows it. Okay. Now, when you put this, right, there is a voltage drop across this, but with the same drop, you technically want to be able to measure any voltage. So what you do is, current here not exceed the maximum deflection. So typically what you want to do is, you want to increase the, so when measuring actual voltage, okay, current in the meter cannot exceed current in meter, current through meter cannot exceed IFS. Cannot exceed IFS. This is obvious because if it exceeds that, the purpose of the meter is lost. The meter cannot go beyond this. So when measuring this, actually, you have to restrict the current. Does anyone know how that current is restricted? That is, how they make sure current doesn't exceed a full scale deflection. In this case, when you just have the meter, let's say, let's ground this, and this voltage is going to be V full scale. There is, setup, just the thing. When you apply this voltage, this is V full scale, 0 is just a subscript, you get maximum deflection here. The relation is just VFS naught equals IR, IFS. If you apply half the voltage, there will be like half the deviation. Deviation will be this. So deviation is proportional to. So this cannot exceed first. So they add something called a shunt. Resistance or yes, shunt resistance. Yes. And the purpose is the current shouldn't exist. So it is added in series so that the net resistance is high. Resistance to current flow is very high. So your circuit looks like this. Color code the meters. No, I didn't. It's added in series. Yes. Okay. And the original meter resistance that is over here. There's internal resistance. Whatever device you put in, that has a resistance. That is our meter. Now, this RS is chosen to make sure you pick a range of voltage, say 0 to 10 or something like that. Sometimes you want to make 0 to 100 volt. You give me the range. 10, there is a shunt I will put. If it is 100, I'll put a shunt I'll pay, such that there is whatever this voltage, maximum voltage in the range that you apply. With that voltage, you get full scale deflection. Getting full scale deflection, that means the current through the meter has to be full scale. Okay. Now, quickly, so what is the relation between variables here? Can you relate? Can you relate? Max is voltmeter range. Well, can you relate Vmax, IFS, and then RM and RS? Meter resistance, the shunt resistance that you put for the given mix. So let me also make a note here. RS is chosen suit max. What is the relation between these four parameters? Apply basic. If I apply a Vmax here, okay, that is at this terminal where I measure, if I apply Vmax, there are two resistances there. The current in it is IFS. Can we relate Vmax, IFS, RM, RS? RM, RS are in series, so they will add and then apply Ohm's law equation. Yeah, that's it. So notice the relation here would be your Vmax max should be equal to IFS to total resistance there, that is RM plus RS. So when there is no shunt added, this is, let me now highlight, this is no shunt scenario. This is no shunt added, no shunt added. In that scenario, specific voltage gives you full scale deflection. What are the relation between VF this VFS not without shunt is just IFS into RM. Straightforward. When you have a shunt added, that V voltage that gives maximum deflection changes. That relation is just V max is IFS, V is IR. Okay, sometimes you can rewrite this, but I feel that is not necessary. Notice this specifically that would imply your RS should be max or RS should be V max IFS plus RM. Okay, you could rewrite this same equation this way, but I suppose whatever I box is straightforward as such. This equation tells you, hey, now if you know full scale deflection, if you know Vmax, if you know RM, I can help you pick the shunt resistance. So give me the voltage range that you're trying to measure. Based on that, I will give you the shunt resistance. So for any other voltage less than that, the current is going to be lesser and then the deflection is going to be this. Yeah, Isha wrote it, Shraddha wrote it. So this is just V is IR, right? So this is fairly simple. This bit is what I wrote here. RS is chosen to suit Vmax, right? You have it in that equation here, right? RS. Once you give me Vmax, I can tell you what is that RS. This is how a voltmeter works. Simple resistive circuit. Just need to understand what is RM, resistance in the meter, what is a shunt resistance, what is this full scale current, and what is this Vmax that you are under. Okay, let's quickly look at PVQ. Okay, you see if this is measurements or circuits. Suppose measurements. Yeah, screen is visible. Just look at the question. Give me like, give me a simple strategy before going to numbers, before going to equations. Look at this. Tell me how you would. This is a very easy question. V is IR. That it only needs that relation, but you need to understand what's what. There's a moving coil voltmeter has an internal resistance of 50 ohms. Scale of the meter is divided into 100 equal divisions. When a potential of 1 volt is applied to the terminals, deflection of 100 divisions is obtained. However, it is designed that when a potential of 500 volt is applied to the terminals, a deflection of 100 division should be obtained. Value of the resistance that needs to be connected in series to achieve this is. Tell me, there are, tell me this lines in terms of the terminology that I just explained. Okay. When they say what does the first line mean? What does the second line mean? What does the third line mean? Put it this way. Okay, let me highlight. So there is an internal resistance of 50. That statement means something. Okay, just tell me in simple English or the terminology that I just explained. Divided into 100 equal divisions. Okay, fine. Then when 1 volt is applied, fraction of 100 divisions is obtained. What does that green mean? And then formulae. So it is if you apply 500 volts, you want 100 division. What does that orange mean? Notice RM. This is your RM is 50 ohms. Then full scale deflection is 100. Fine. That is correct. This is okay. Let me. This is full scale. This is full scale. Very good. Someone else, Shraddha is now decoding it. Someone else, can you decode it? So this is full scale. Is there a word? Do we know full scale current? We need to know IFS to find, let's say, the shunt or something like that. And the value of the resistance that needs to be connected in series. Of course, now they are referring to the shunt. Okay, let me put it this way. RS. So this can give me full scale current. Okay, the green and this thing. V is IR. Okay, I can easily get the full scale current from that. Okay, notice EFS is 1 by 50. V by R. I got the full scale current. So on SI, so I'm not explicitly writing the units. Okay, fine, amps. I got the full scale current from that. So we know RM, IFS. So what is this orange thing? 500 volts. So now this is your Vmax. So that, again at 500 you want full scale. So this is Vmax. See, at 500 if it says, let's say 50. This is Vmax by 2. But it says at 500 you want 100. So this is Vmax. Hundred full scale deflection. No. Yeah, when they want 100 full scale, that is, they want full scale deflection at 500 volts now. Scale. Now, let me in fact slightly write it. Notice full scale new Vmax. So we have to modify it. Yeah, they are asking for the shunt resistance. So one equation I already got it. Now, what is the circuit? Let me also remind what the circuit is. No, you could put it this way, and then you can say this is grounded, or I'm grounding it here itself. Grounding is, I'm setting that as a reference. Okay. There is RM. Okay, let's again, let's use our color code. RM. I'm going to put a R shunt, so that now my 500 volts. Okay, I get full scale deflection. This is 500, and I get full scale deflection. That means my current here is full scale, that I just found out to be 1 by 50. The current value. Let me write it in our standard form. This is max RM RS IFS. Given any 3, we can find the other. This is given, this is given, this is given. They want you to find this. What is the equation? This is fairly straightforward. V max is Fs into Rm plus Rs. Can you tell me what is Rs? The answer in ohms. I already wrote down what is what. Can you just substitute and find out? So notice IFS is 1 over 50. This is known. This is Vmax is 500. The three values are known. This is 500. This is known. This is known. If you want me to. Four, 50. I think that is correct. So that is 500 into 50 minus 24950. Okay. Now, so there is a question on measuring voltmeter. Okay. So 500 into 50, 25,000 minus 50, right? So this is a way to measure current. Notice this RS is added in series because you are trying to limit IFS. Sometimes it's confusing. Yeah, RS added series or parallel. Voltmeter, you are trying to limit IFS. RS, you increase the net resistance, so RS is added in series. Okay. What happens in ammeter? That meter that you use is essentially the same. This is the D arsenal meter. Okay. But how you use it is different. Now full scale current, there's deflection is maximum, but whether that responds to measures voltage or current is now different. So going back to that, this is a voltmeter, right? We discussed this quickly, somewhat. We'll do ammeter somewhat fast. Ammeter. So circuit is this. Same meter. It's a full scale current in the meter. There is again a current that gives you full scale deflection. Kind of an element is this. So notice so the current through the meter is IFS. How do you represent this? Same thing. It's essentially the same meter. Okay. So you have a resistance and there is a R meter. You have I plus some. Full scale meter current. Full scale meter current. Full scale current, it's full scale meter current. This is FSM, IFS. Now, here, okay, you're trying to limit the current, but the total current that is drawn cannot change. Total current drawn cannot change. So that is what you're trying to measure. If you're trying to measure voltage, so the current could change, only the voltage shouldn't change. But now, if you put something in series, the total current drawn will change. Okay? So, the way you shunt this, okay, so ammeters are shunted in parallel. So this is a circuit that you have IFSM, have RM. Now this is modified into this. So again, the current through the meter remains the same, but you should be able to draw any amount of current. Provide an alternative path for current to flow. This is still IFS. So if you are sending a different current to measure, provide a alternate path. Let's say whatever, say I'm trying to measure I. Okay, this is the maximum current in the range that we are trying to measure. In that case, what we should do is we should provide it an alternate path, so that most of the current will go through that path. What goes here is IFS. So the current, net current drawn is current that you want, that you are trying to measure in a specific range. Now you still send IFSM through the meter of interest. The net current drawn is now Imax. You give it a parallel path. That is your shunt. Okay. So Imax is current, is maximum current in the measurement range. Is max current measurement range. That is, in other words, max results in full scale deflection with the shunt. Results in scale deflection. Shunt. RS. RS is chosen according to this. RS chosen based on what you are trying to measure. So RS is chosen based on Imax. Same as before. But we had a series circuit there. Voltmeter. Ammeter, we have a parallel circuit. What is the relation between these four? The relation between now Imax, IFSM, RS, RM. Anyone write down the relation? Look at it. In simple sum, KVL, KCL will give you. Now these are two parallel resistors. So what is the same across them? So most of the current is now going through this path. Imax enters, some of it IFSM goes here, the rest goes through this. Okay. What is the relation between these four variables? The same net voltage. Voltage across the two resistors, V, same V, because they are parallel. Voltage across RM should be the voltage across RS. So that is the relation. Can you give that? So now you could write this in two ways. Write this current division. IFSM, current through the meter that gives full scale deflection. The fraction of Imax, not Imax theta, this is that gives maximum deflection in the meter. It's a fraction of that. What fraction? This depends on RS by S plus R. Or equivalently, yeah, that is correct. Or equivalently, notice IFSM into RM is rest of the current into RS. It's slightly decrease. So let me write down that relation. Notice this is or equivalently IFSM to RM, that is a voltage drop across resistor, that should be equivalent to rest of the current, that is Imax minus IFSM. Okay, this current to resistance, that is RS. Again, we got to a stage where give me any three, I can tell you the other. On a typical application perspective, I'll tell you the current I am going to measure is in this range. Imax, this is the range that I am trying to measure. With this meter, can you tell me, help me choose a shunt resistance? Can you find RS? That is a practical problem. So given any three, you can find the other. But finding the shunt resistance is a practical problem in a ammeter. See, Notice in reality you can have a switch here that changes across three resistors. So the ammeter circuit will show you three resistors, based on the range. Is it 0 to 10, 0 to uh, you know uh, ze- uh, say 0 to 10 millivolts, 0 to 100 millivolts, 0 to 1 amps, right? So there is a minor switch that shift between resistors, but this is a circuit. Okay, let's look at an example. Let me give you something that is realistic. Meter example. Full scale meter current. Say this is 1 milliamps. Meter resistance. Let's say this is okay, something nominal. Okay, again 50 ohms. Okay. Now current range, required current range, required current measurement range is, let's say, 0 to now should be the what RS, what shunt resistance should be connected in parallel. Now they can ask you what shunt RS should be connected, whether it should be parallel series also they can ask. Yeah, I'll give you like 45, 1 minute, 1 minute, 45 second. My timer is missing, but I'll give you about a minute and a half. You want me to show the circuit? The first sum is 1 milliamps, RM is 50, I max is 1. Can you find it? Can help it, write it here. In that example that we are looking at, this is 1 milliamps, 1 amps, and this is 50 ohms. Can you find RS? So that is, bridges are done, voltmeter is done, ammeter is done. Now we'll do transient circuits. Okay, fine. Let me show the question. I thought the diagram will be useful. Okay, this is now more than a minute or so. See, notice you are sending 1 amps. A small current should go through the meter. That means most of the current should go through RS. That means RS resistance should be much smaller. Sounds good. Mugdha is wondering whether a 0.05 is sensible. I have to solve for it. But you're sending 1 amps. Your tiny fraction should go through RM. That means RS is very, very small compared to RM. So most of the current is going through RS. So this is 50. RS is a fraction of 50. 0.05 is sensible. Okay, let's solve that. Okay, let me erase this bits here. Let me redraw it there. Okay, now you got your max. When I send I max, the current through this is IFSM. So this is RM. Of the current go through the shunt, and what goes through here is max minus FSM. Okay, so now max into RM. You have to remember that. You can write it down. I max minus IFSM to RS. So if you change that to numbers, you have 1 into 50 equals 1 minus power minus 3 into RS. That implies your RS. So now that is 50 divided by minus 0.999. 0.999. Oh, something is off. Minus full scale is correct. T divided by 1. Yeah, this is now I'm getting approximately 50. Yeah, now this is really stupid of me. This is IFSM. 10 power minus. Yeah, now what is your RS? 50 into 10 power minus 3 divided by 0.999. See, notice one is I knew the answer was I got 50.5. So shunt is same order as RM. I knew something was off. There was a red flag because the same explanation I gave you. Sending 1 amps, a small current goes through RM. That means RM should be very high compared to RS. I was getting small same value, so this is why I quickly that red flag detector, right? Any number I get, I typically without solving it, does it make sense? That question I ask. In this case, I figured out the issue by that. What I get is 0.0500. So 0.05. So let me again put this in perspective. Whatever I was trying. 1 milliamp of 1 amp goes through that implies RM very higher than RS, because a small current goes through RM. That means the resistance of RM is very high. That is why, in fact, at the first place we are adding a shunt. So this logic helped me catch that issue. Okay, fine. Current division also should technically give the same result. So this is, you current division, this is, you rewrite this, you get current division. Okay, separate IFSM, that is current division. But this is how you get current division to start with. Let me also show that. We take that, take the dagger, FSM RM, take that RS to this side. Yeah, so now my FSM is fraction of I max. That fraction happens to be RS by RM plus. So I didn't show, the current division formula, but you're saying, hey, what is same? Voltage is the same, then current splits, right? Use that logic, you get that. Done. Done. Bridge circuits is important because this at the intersection of circuits and measurements. This is also, at least every 2 years there is a question. There is, it's like tossing a coin, head or tails, right? Probability of that, there is a probability of getting a question here. Okay, because this is at the intersection of circuits and measurements. Application of circuits and measurements. Okay, and be careful. That is, if this is, if this IFSM is, I gave you full scale meter current as 1 milliamps. This information could be given differently. That is 0.5 milliamps gives half the deflection, half the total deflection. That means 1 milliamps gives full scale deflection. It could be given that way. So if this is 100 divisions, 1 milliamps gives 100 divisions. And then they get, here I told you, your measurement range is 0 to 1 amp. So I told you what you're trying to measure maximum current is 1 amps. Right? They can tell you 1 amp should give me 50 divisions out of 100 divisions. That also they can give. So 1 amp should give you 50 divisions. In total, there are 100 divisions. That means total 100 divisions. This implies now your maximum current that you're trying to measure is 2 amps. 2 amps gives 100 divisions, right? They can slight wordplay in how they describe full scale meter current. Either they can say 5 milliamps gives half the deflection, half the full scale deflection. By that they mean full scale meter current is 1 milliamps. They can make a change in this side. Can also make a change in this side. Instead of saying the range is 0 to 1 amps, they can say, hey, with 1 amp, we want to get 50 divisions out of 100. So total divisions is, say it's 100, total divisions 100. So maximum current we are trying to measure is 2 amps. So that wordplay, there is a subtle footwork there. Be prepared to make that question. It doesn't make the question hard. It's still moderate, but be prepared to handle that change in pace. Okay, change of pace. In fact, if we have to give you the same 1 amp, they can tell you 0.5 amps. Give 50 divisions. Total is 100 divisions. So again, they are referring to I maxes. Amps. Be prepared with this weight plane. They could have given you this information instead of this, or this information instead of this. Two equivalent things.